Cool. Okay, let's go ahead and get started. Sorry that we didn't have any music today. The sound was being a little bit weird. But today's lecture is going to be a layout tutorial. Basically, we were looking through, well, layout is due tomorrow, and we were looking through everyone's Altium 365 because we can snoop. And we realized that people are a lot farther behind than we wanted. And so the purpose of today's lecture is going to just be walking through layout a little bit. You guys are going to guide me and tell me what parts of the board we're going to work on and how we place parts and put everything together there. But the purpose of today's lecture is just to get you more comfortable with how to tackle the big problem that is the layout, because that is the big core deliverable of the class, and we want to make sure that you feel comfortable with the Bluetooth speaker and also just for all of the PCB design you're going to do in the future. So that's the purpose of today. I'm going to sit down and basically start doing layout from scratch. And y'all are going to tell me parts that you're confused about, and then I'll just narrate the bit, and we will walk through how everything goes together. Before we do that, we've got some announcements. Board layout is due tomorrow. Depending on how things go with people's progress and stuff, we might have some flexibility there, but genuinely, we're just running out of time in IAP. So we're going to do our best there. We might make some changes, but for now, proceed as though layout is due tomorrow. We also have track 2 DRs going on. We didn't have any on Monday, so the first ones are starting up after lecture. If you did not sign up for a track 2 slot, you've been contacted. And if you did not hear from me, you should let me know, and we'll make sure you're in the right spot. We also, since we're approaching the end of IAP, make sure to triple check your registration. Make sure you're registered for the number of units that you want, under the course number that you want. Everything is graded PDF because that's the constraint that we have from the registrar. So just make sure you're signed up for what you'd like, because it's a lot easier to submit add drop forms now rather than try and go back and rewrite your transcript right before IAP ends. So triple check that. It's IAP, so add drop forms do not require any instructor approval, I believe, or any advisor approval. So it's literally just you push a couple buttons and then it automatically goes through. So please be on top of that. To make things easier on us and easier on you. Cool. There's a couple other things. I had a chat with some of the Altium folks the other day, and they wanted to mention that they have a scholarship available for women and some other other minorities for a little training course called Altium Designer Essentials, and it's basically an intro course that is very similar to what we've done here, except it's more focused on Altium as a tool, more so than circuit board layout as a concept. And it's basically it's some offline content, and then it's a 3-hour webinar that comes afterwards. And you can see that is about how much they charge the average person for it. And they want to make this freely available for a handful of people. If they ask for 15 or so. So if this is something that sounds interesting to y'all, you want to get more information about the tool directly from the horse's mouth, let me know. Shoot me an email, and probably by the end of IAP, we're going to send them a list of names, and this is available to you for free. I personally have not gone through this myself yet. I'm going to before we send y'all's names off, just to make sure that it all holds water. But if this is something that interests you, let us know. We'd love to fire your names off there. Cool. Only other thing I have to mention is that a week from today, we're going to have pizza, music, some good vibes in Lobby 13 at around 6 p.m. Be there, be square. We recognize that you all have put a lot of work into the class, and we want to celebrate that, give you all some food, and generally just have a good time.
Bring your friends.
Bring friends. And then also for next week, this is the general structure of what things are going to look like. Monday, we're going to give our last lecture. It's something that Aditya and I have been thinking about for a while now. It's called Hardware is Not Dead. And it's basically just a love letter to hardware and why we care so much about this. And then that's going to be our last lecture. So then Tuesday and Thursday, we're just going to be munching away on Lab 4, making sure that we get your Bluetooth speakers as close to working as we can. We'll also just have some general office hours then if people have questions, if you're track 2 folks, or just questions in general. Wednesday is food, of course, and we're also going to leave it as a Slack day. So if there's any extenuating circumstances that you have that we don't know about, please tell us as soon as possible, because we want to make sure that we have time booked out to help you on Wednesday next week. And then Friday, Addy and I are going to do grades, fill out all of our paperwork, and then go get some sleep. Cool. Any questions about this for the moment? Excellent. OK, so with that, we're going to jump into doing layout from scratch. I basically took the, let me grab a chair for this. I basically took the Lab 2 schematic final solution and then grabbed that into an Altium project and then just have a blank circuit board for it. There is nothing here. I have no parts imported. It's literally just blank. What do y'all want to see laid out? I'll go ahead and pull all the components in, but is there any particular schematic or room or anything that's causing y'all trouble, or is it just a general how do I start, where do I go kind of thing? Sure, okay. What else are people thinking about doing layout? Huh? Okay, we can talk about that a bit. Yes, okay. Anything else that's on y'all's minds? We're gonna try and wrap this up into a nice, delightful little package in the next little bit. Yes? When you say trace guidelines? Yes, how do you make those happy? Okay, cool. Anything else? Yes. Yeah. Ground connects everything. How do we route it in a way that doesn't make us go insane? Mm-hmm. Okay, cool. We can talk about that. Anything else? Just so I can get a temperature reading on the room before we jump into stuff. Okay, we'll work with that for the moment. I'm just gonna start by pulling all the components in. I'm gonna use some keyboard shortcuts here. I'm gonna try and do my best to narrate them. I'm gonna hit D for design, and then I for import changes. It's basically the same as if you went to the design menu and hit the same thing. This is just gonna pull everything in from the schematic. We'll hit validate. We shouldn't have any errors here because we're just pulling everything in for the first time. These are going to complain because it's trying to make nets into differential pairs, but those nets don't exist on the board yet. So if we hit execute, these will actually all be green check marks over here. And this will take a little bit because we're adding literally the entire board, or all the parts to the board. Cool, so now those were all red before, now they're green. Excellent. So, all right, let me make sure I don't mess up Mac shortcuts. Okay. Great. So this is what we get when we pull everything into the board, right? Let's go ahead and I want to address your question of how do you route power relative to the DAC and whatnot. But I want to do that with a just general how do you place rooms and whatnot. And I think we're just going to start by taking a room and then pulling it out and making it into something that we can place on the board. Looks clean, and then we'll start playing Tetris with the larger rooms. So that's a lot of words to explain something that'll hopefully be made a little bit clearer here in a second. Let's aim a little bit big. Let's route the largest room. Which one is that on our schematic? What has the most amount of parts in it? A little bit louder. It's not your question. The amplifier, right? At least the power has a lot of stuff going on in it too, but at least in terms of number of components, amplifier is loaded. So we're gonna take that and run with it. So if we go over to our PCB here, like we have all of our schematics here are represented as rooms. The rooms are these like big purple blocks, and everything in that room is just all the parts from that schematic, right? So like inside of our amplifier room down here, can you all see the text there okay? Okay, let's zoom in a little bit. In order to zoom, I'm using like V and then I for view and then zoom in. And so if we like look a bit here, this says like U amplifier. So that's our amplifier room. Let's go ahead and try and route that. And I'm just going to buy us a little bit of space. And I'm going to try and move the room. Here it's complaining because it doesn't know what to do with objects that like aren't assigned to any like net, meaning they don't have any electrical connection. We shouldn't have any of those, so we don't actually care. And it's also wondering what to do with locked objects, where we have locked its position. We just grabbed everything and just dumped it into the board just now, so we shouldn't have any of those. So I'm going to tell it to just don't ask me about it again. We'll worry about that later. OK, great. I have this room. I'm going to move it up here. We don't have to put stuff on the board immediately. Like we have all of this free like real estate surrounding like this light gray area over here. So I'm not going to like be worried about the board or my size just yet. We're just going to like route the room. And these components probably aren't going to take a super like linear fashion on the actual board. So let's just buy ourselves a little bit of extra space so it's not just like a pencil of components. Cool. So let's have a look at our amplifier schematic. So when we're doing layout, we want components that are electrically connected together to be physically close together, right? Because that means we have to route really short wires between everything. Well, conveniently, we needed to figure out what components are electrically connected to each other when we were making the schematic, right? Like in order to draw all the lines and stuff. This is like a reasonably neat schematic. It's not perfect, but all the stuff is like reasonably close together, right? So if we were to zoom in, we could say like, hey, coming out of pin 30 on the amplifier, like on the amplifier chip, we have C18, C19, R16, all in a line. What would be a logical like thing to do in the layout now that we've seen that this is the case in the schematic? Yeah, we should like have all of those reasonably close to each other. So let's do that. Let's go over to the board, and we just have this massive line of components, and we want to find C18, C19, R16. Well, we could zoom in and try and find everything here, but we also have a convenient tool that will just take us to where those parts are. So let's say we want to find C19. I'm going to hit J for jump to, and then C for component. And I'm going to type in the designator that I want to find, so C19. And then my cursor has now been moved up here. And let's go ahead and zoom in on that. Oh, hey, C19. Delightful. OK, so let's go ahead and grab that. And then what other parts do we need in addition to C19? What are its friends? What goes along with it? Yeah, so 18 and 16, right? Interesting. 18, 19, and 16 are all right next to each other there. That's because when Altium loads stuff into your circuit board, it just like steps through your schematic, and things that are physically close to each other get dropped physically close to each other in the layout. It's great. Cool, so let's take that, and those are going to be a little bunch of friends, and they're going to live over there. Cool. And so we can take a closer look at these, and maybe like, sure, in the schematic we have them as a straight line. Let's see if that's the optimal like arrangement for them here. OK, if we zoom in, we can see the net name on each of these parts. Can you all see the text like right there? Cool. So this pad on C18 is going to want to be connected to the net called out-RP. This is the positive side of the right output channel for our speaker, right? We have like two speakers, a left one and a right one, because we have stereo audio. And this is the positive side of the right one. So that wants to be connected to a bunch of stuff. I'm going to hit Control and then left click, if it'll let me. Never mind. And well, we can see that like this pad over here wants to be connected to this pad. So what's a logical thing to do to C18 in order to make that happen? Huh? Yeah, just rotate it. Okay, so let's do that. Boop, boop. Layout's more fun when you make noises for it. So we just boop, boop that component over, and then excellent. The wire that needs to connect these two is now super short instead of having to route around this whole thing. Is there any other optimization that we could do to this set of components? Yeah, we're going to do the same trick for R16. We'll flip that over. Excellent. And so now these are just straight up in a line, and well, that kind of makes sense because, oh, hey, we're doing the exact same thing here. Whoa, crazy. Yeah, what's up? That's an excellent question. I believe that the way, correct me if I'm wrong, teaching staff, but if you manually like drag and change the like text position, and then like if I manually move this, whoops, if I manually move like the C18 label or something, like over here, then Altium will be like, oh, you want C18 to have like that kind of offset relative to the part. And then now if I like move the part again, now my text will also rotate. But that's because we told Altium that like, hi, we want this offset with the text here, but if we don't give it that, then it's like, sure, I'll just keep it like flat. Does that make sense? Cool, so I just hit Control Z a couple times, and now if we rotate it, now it doesn't care. Cool, so this makes us want to place parts first, and then move texts around later, which kind of makes sense for how we do layout. Does that check out? Cool. Okay, so let's try and do the same thing for the rest of our parts here. So 24, 25, 17 form a line. So let's just not even bother with the flipping. Let's just go ahead and just bunch them together. Cool. So what's our trick for finding the right part? JC, right? And then let's look for C25. Oh, hey, it's right here. 24, 25, R17. Great. I'm not even going to bother orienting them correctly. I'm just going to drag them and put them down here. Okay, so then what's our next set? C27, C28, R18. Okay, so we'll do the same trick. Oh, we can also just notice that they're right here as well. So we'll grab those, drag them down. And if you notice, like all of the little like the super thin gray lines through here, those are called air wires because those are wires that have to be connected, but they haven't been routed yet, so they're just flying through the air. Also called a rat's nest for obvious reasons. Another way we can look at these and see what connections have to be made here, and there's also another way we could orient these as well. Like we could go ahead and maybe drag this part over here, and then maybe this one goes over here. And then when we actually went to put copper down, we would connect these two pads and then these two pads. So many possible configurations can exist. We might want this one versus the other one for maybe because we're just trying to optimize space. Maybe this one fits better, whatever. The parts don't care, like as long as you make the right connection. Cool. So let's go ahead and grab the last set. 30, 32, and 20. And let's see if we can find it. Oh, here we go. And we'll grab that and we'll just drag it down. Again, I'm not going to like bother with like putting it in the right orientation. Cool. That looks good to me. And then let's go back and take a look at our amplifier schematic. What do we notice about the like numbers over here as they come back around? They seem to have like some kind of order to them, right? Like we start at pin 1 over here, and then 2, 3, 4, 5, we loop back around. And there's some weird stuff that happens over here, but we go like 16, and then back up the side, 17, 18, 19, 20, 21, and so on. This is because when we label the pin numbers on parts, we usually start in the top corner and then go around the side. And we can actually see that inside of the like part itself. Here is our amplifier chip, right? But if we like zoom in even farther, we can actually see what the pin number is here and what net it's connected to. So here, this is pin 1 is connected to ground. And if we keep scrolling, we can see what all of these are connected to. Some of these are auto-generated, like net C33 underbar 2. That's auto-generated by Altium. But some of them we put there, right? Like we told it that this is going to be pin AM0, right? So you'll see that. The last pin on this side is pin 16. And since this part is like the same on both sides, what does that mean our largest pin number will be? 32, right? And we can see that. Over on this side. Excellent. Pin 32 goes over there. Great. So let's try and see how the chip itself lives in regards to our little groups of 3 parts over here. Cool. Which side of the chip should it live on? Now that we know this. Left side, right side. It should live on the right side, right? So what we'll do is we'll take the chip, and let's just try and get the board layout to reflect that. Let's just drag it over here, and then hey, look what happens. We have a lot more of our rat's nest pointing from these output pins over here to our little groups of 3 parts over here. Okay, great. We're starting to untangle this a little bit. Cool. Let's just finish building out the right side of our amplifier, maybe. Because it's actually a pretty linear progression. We have these little bits on the output, and then we have this little output chunk, right? So let's try and like build those in. We can start from the top, I guess. Let's go ahead and grab L1, C17, R12, C20. And if Altium did its job right, those should all be like fairly close to each other. Let's see if we can find L1. I'm going to use JC again because I don't immediately see it. OK, it's over here. And then, all right, we wanted L1, and then what other parts? L1, C17, 12, 20. OK, we're also going to we'll want most of this and also this guy over here. I'm holding down like Shift in order to select multiple parts at the same time. Cool, so we got this. And this guy should come over here, and if we zoom in a little bit, oh, sorry. As we drag this around, we can kind of see where our air wires like want it to point to. I don't know if you can see that in the like projector, but the air wires are kind of pointing to R16 a little bit, right? So we're going to try and put it over there. Cool. So let's just go ahead and get all of this like nice and cozy. I'll grab all these parts again. We'll go over here, and maybe we do it like this, because we have all the stuff on one side of the inductor and all the stuff on the other side of the inductor. OK, cool. Let's try and clean this up a little bit. Because we have everything in basically the right spot. We just need to like flip it all around so that it looks good. Let's see how to do that. Well, on one side of the inductor, we have RP, and on the other side, we have out RP. Let's see what that goes to in the schematic. OK, RP should be on the like right-hand side of the board. So let's just flip the inductor in order to like show that that's the case. So we'll do that, and I accidentally took the other parts with us. Let's get rid of those. OK, we'll just flip that around there. And then cool. Let's see what the best way to route RP is over on this side. Well, maybe we put this resistor here, and then maybe this resistor goes there. So then we could just route like RP like over and then down. And then maybe this capacitor can live up here because these two pads right here are trying to connect. Does that seem reasonable? Like just as a first pass? Cool. That's just kind of the mindset you want to get into. Is like, it doesn't have to be perfect right now. Like, you know, I have my silk screen on top of the actual part. I can't fabricate that. But what matters right now is placement. I just want to make sure that all the placement's good so that when we go to route, everything is super tight. Is this useful thus far? Is this helpful? OK. I'll take nods and thumbs up as a green light to keep going. OK, so let's do the same on the other side. And I'm trying really hard here to not just reinvent the layout that I already did for this. But let's see. OK, this is out RP. Where do we have that on this network? OK, it's on these two parts. Out RP is here and here. Let's go ahead and just put those closer to the actual inductor a bit. And maybe we want to get crazy, and we'll just rotate it like this. So maybe in order to make this connection, this then becomes a T of like a T-shaped piece of copper. Okay, and then we'll maybe up top here, like we go ahead and flip that one around too in order to produce something that looks like this. So then now these two nets here and here that want to be like next to each other, they stay there. Cool. And then maybe this whole thing is like not super well aligned. It doesn't look very pretty. So maybe we just drag this down here. And cool. If we were to go to route this, what we'd want to do is, let me see if I can get this to work. When you're routing your boards, you have something called a selection filter, which basically dictates the kinds of things that your cursor can select. And it lives up here, up by this little filter. If we click the drop-down, this will tell us all the things that our cursor will activate. I'm going to turn them all off right now, because I don't want to touch anything other than text. I'm going to move all these texts around so that I can like make a little bit of a point. And theoretically, if I fix the bug, nope. Come on. Texts. Okay, there we go. Perfect. Let's go ahead and move all these texts. We'll move the ones on this side, maybe over here. And then we'll take the ones on this side, stick them over here. And then when we actually go to route this, we're going to use Control-W to start routing. That's the shortcut for it, and it is very handy. And if you notice down on the bottom here, I don't know if you can see the text, but you see how like it says my top layer is activated, like on this super bottom part of the screen, like right around here. That's telling you what layer you're currently routing on. And it also tells it to you over here. Cool. So let's say I want to go ahead and route this board. Whoops, I clicked in the wrong spot. Let's go ahead and route C19 over here to this other side of the resistor, because we placed them super close. And it'll highlight in red, it'll highlight the part that you want your trace to go to. So we'll go over there, and then we'll take this one, and like this doesn't need to connect to anything else over here. So if I try and like get it over here to connect to it, Altium won't let me. It'll try and like put the like trace in the right spot, but it won't ever connect to something that I don't want it to. So it really, it tries to help you like not mess up here. But cool. All right, that was two things that I need to connect. Let's try connecting three. So I'm going to click on the top side of this capacitor, and then we're going to go to C19 in order to connect that, and then we'll connect that part to the other side of the inductor here. Excellent. And we can do the exact same on the other side. We can go over here, and then we put that there, and we could even route this part like a little crossways too. Cool. How long did routing take? 30 seconds, tops, right? How long did placement take? A couple minutes. The reason being is because this is now super nice and tight and well packaged, and we can move this around wherever. Placement takes a long time, because it takes us a little bit to figure out, okay, this is how these parts are structured in the schematic, and maybe that informs how we should put them into the layout. It takes us a little bit to figure that out. But once we do, the actual connections between them are super short and really straightforward. Does that hopefully make sense? Like, we've been like telling you this in slides and asking you to believe it for the longest time. But is that something you can like see yourself believing? Okay, cool. Excellent. So once we do that, let's say that we route the other like 3 copies of this in much the same way. Well, let's get all of these guys out. And actually, I can't select them because I can only select texts right now. So let's change that. And let's just move these out of the way. Okay, so then we'll take that, and we'll move these maybe a little bit closer to the chip. Okay, great. So that's one of our little output stages. We're going to have 4 of them. There's 4 inductors and whatnot. So we'll route the rest of these the same. And I'm not going to do that right now because you've already seen the trick. And then maybe we'll take a look at what's on the output of these on the output of these little networks. And it's the connectors that go that actually connect to the speaker itself. So that's going to be like J2 and J3. So we'll go ahead and just like pop maybe J2 over here. And maybe J3 will go down here. Something like that. And then so that's our left and our right channel. This looks a lot like the board that we gave you, because this is kind of the way that like Texas Instruments wants this chip to be routed. When you start looking at like chips that do a lot of stuff all at once and have some high complexity associated with them, usually they give you a guide for like how you actually route the part. Sometimes that's in the data sheet. Sometimes if they need more explanation for it, they'll make another document called a application note or an app note that will tell you like the specifics of what you're what you should be doing. But cool. So the trick here was to route a bunch of small stuff, put it together, and then play Tetris with like this block we just made here, and then like stick it next to the chip. Cool. If we wanted to do this for the rest of the amplifier, we could, this is only half of it. We could start turning our attention to things like the bypass capacitors, which we talked about the importance of in lecture because like they need to reject noise from the circuit. So our bypass capacitors, we have 2 sets on this part because it's audio. If there's any noise in there, we'll hear it. So C42, C47, C48 are one set, and then on the other side we have C49, C50, C51. So let's see where those like physically live on the chip itself. Let's see if we can find these on the board. And how are we going to find our parts? JC, right? So C42. Oh, hey, Altium put all of these right next to each other for us. That's super convenient. Let's just go ahead and grab that. And again, I'm not going to worry about like finding the optimum like orientation for everything right now. I'm just going to drag it like near where it should be. Cool. And since all these connect to pin 32, we know that's on the upper left-hand side, or sorry, upper right-hand side of the chip. So we'll put that up there. And if you notice, 12 volts is the top side of this thing, and we want that to be close to the chip. So we'll just flip the whole thing around. And okay, we've just made that a lot. We just put our bypass caps in roughly the right spot. We can do the same for the other set of bypass caps. If we look over here, we can see that pins 17, 18, 19 do the trick for us on the other side. Where on the chip will these pins be? Yeah, the bottom left-hand side. So we'll just go ahead and do the same thing there. I forgot what the designator is. Okay, C51 is what we'll look for. Excellent. Okay, so we'll just grab these. And then, again, we want 12 volts to be near the chip. And we notice, okay, 12 volts is the pad up there. We'll take this and then just drag it over there. Again, I don't really care right now that like there's the silk screen kind of like just colliding with everything. That's easy to fix later. What we care about right now is that our like rat's nest gets like tamed. We want that to be nice and we want that to be less complicated so that our routing is easier to do. Cool. So there's our bypass caps roughly set. They don't need to be this far apart, and they really shouldn't. So let's say that I want to pack it in a little bit more. We could go ahead and stick this. We can put our text up a little bit on the side so we can pack everything in a little bit tighter. And we'll put that there. We want to pack it tight so that we are better able to reject the noise that comes in. The farther away the caps are, the more copper we use, that makes an antenna that can send and receive noise. So we want it to be as short as we can. So we'll do that, and we'll bring these a little bit closer. And having smaller boards also makes them cheaper, as you all discovered on Lab 3. I made them too small, sorry about that. But that will reduce cost, which is something that we appreciate. Okay, so all of these are like all close together, and we can just route that down next to the chip itself, and excellent. So when we go to actually route this, let me see if I can figure out what the right shortcut is. Okay, it's a little weird because I'm on a Mac. But if you hit Control and then click the 12-volt thing here, it'll highlight everything that's 12 volts on the board. So you might just have to take my word for it for right now. But if we wanted to route this, again, it would be super straightforward now that we did our placement properly. Like, we can route all 3 of these parts together in one go, and then we just whack this up here, and excellent. We've now routed 12 volts for this part. All of our bypass caps are good. We're done. Yeah? What do you mean using shift and hovering over? Okay. Oh yeah, that does help. Yeah, that basically does a very similar thing to like control clicking. But yeah, feel free to use whatever like visualization like makes your job the easiest. Cool. So there's that. We can like continue to pack these in, make it like nice and pretty. Let's turn our attention a little bit to the right side of the chip. If we look at our rat's nest here, or sorry, the left side of the chip. If we look at our rat's nest here, we can see that there's a lot of parts that are like over on this side that we want to connect to that half of the chip. So let's go ahead and like just grab a couple of them and just bring them over. I'm not even going to bother looking at the schematic for this one. We're just going to take them and just come over here, and we're going to kind of let the rat's nest guide us a little bit here. So we'll whack that in there, and let's see if we can pick a direction for all of these that makes the rat's nest the happiest. What we're looking for is like nice straight parallel lines between everything here, and sure, that'll work for now. Okay, so if I hover over, okay, let's start just bringing these over. If we take one like so and bring it over towards the side of the chip, when we go to move it, it'll tell us where this part should go. The projector might not be doing us many favors here, but can you see there's 2 little like air wires that are trying to get this part over onto the side? If I wiggle it, do they seem a little more obvious? I promise they're there. You'll see them when you go to routing. Actually, let me see if it's made better if I delete the room. You can also delete rooms if you so desire. Yeah, Altium will try and put them back sometimes, but like you're totally okay to delete them. Is that any better? Can you see that? Okay, great. So cool. There are 2 pins here we're trying to make contact with, GVDD and gain SLV. All right, we'll just put that close by for now and not worry about it too much. And maybe we try and like park all the parts in the side of it. Okay, I'll drag the text over here so that we have like some space to work. But let's grab another part. Okay, given that our air wires are like this, should this go on the top or the bottom of R22? Top or bottom? Top, right? Because if we zoom in, if we zoom in, we can see that our air wires want us to connect to a pin that is above the pin that R22 is trying to connect to. So then, okay, when we would go to route this, this would then look something like so. Again, we placed everything intelligently, so now when we want to route these are just directly across from each other. And hey, what do you know? GVDD is on the other side of both of these resistors, so we can just route it like that. Excellent. Super short traces, but all of our time went into placement. Very little of our time went into routing. Cool. So we could repeat that for the remaining side of that chip. And then we could do that, bundle everything up inside of our amplifier schematic, make it nice and tight, make it nice and pretty, and then we can start playing like Tetris with where that lives on the board. Can make it like we basically just turn it into like some kind of a block, and then we do the same for all the other like rooms on the board, and then we just play Tetris with those. If you notice, the recurring theme here is start with something small, like we started just with those 3 resistors. We started just with these at the very beginning. And then we just built up into larger and larger chunks, and then started playing Tetris with those chunks. That's going to be our guiding philosophy for routing this whole thing. Cool. Is that something that sits right inside y'all's spirits? Okay, cool. What other questions do you have? There's some talk of ground planes and other things, but yeah, what's up? Oh, that's a good question. So we have, if you look on here, you see this little like pink outline around the part. That is how much space the resistor will or capacitor will physically occupy. If we were to try and like put these on top of each other like that, I couldn't fabricate that because they're now physically colliding. We also have like a little bit of this like yellow line on there for silkscreen to say that like a resistor goes here. So I don't know, a spacing of something like this would be pretty reasonable. I wouldn't go much smaller than it because if I put these two over each other, yeah, like the resistors will probably be okay next to each other. But like now it's really confusing when I look at the silkscreen because I don't know like, all right, are there two resistors here? Is there one? What's going on? And you can see that a little bit if you push the 3 button and go to 3D view. Right now it's gonna look a little weird because we are not on the board itself. There's like, these are just floating out in midair. But 3D view is really, really handy for just making sure that things don't look stupid. If you want it 3D view, hit the number 3 on your keyboard. If you want 2D view, hit the number 2. Cool, does that hopefully answer your question? Sweet. You had one too. Yes. Let's go ahead and see if we can find a differential pair. So if I did this one correctly, let's take a look at USB because that's got some differential pairs. And the USB connector I'm going to drag over here because it routes to the this little like converter chip, right? Let's just take both of these and throw them on the board for the sake of argument. Let's drag those. Oh. It seems to be grabbing something else, so I'm just going to pick components, because these are both components. We'll just drag them over there. And these are going to turn green because I took them outside of their room. We don't really care about that right now, so what I'm going to do is go to Tools, and just hit Reset Error Markers. That'll clear the green bits. Cool, so let's just route that over here, and then the keyboard shortcut for that is TM, by the way. Okay, so we'll just like stick these two right here. Okay, and then where's our differential pairs inside the connector? Well, it's here and here. So if I hit Control W and try and route one of these on its own, like it seems to be like more than okay to let us do that for whatever. But that's not really what we want to do. We want to route it as a differential pair. So what we do is we go up to the little like box here, you right click it, and then normally it's set to interactive routing, but we want to change it to interactive differential pair routing, and so we'll do both of them at the same time, and then it's exactly the same. You go here, and then both of these traces want to go up to here, and you route it just the same. This one is a little spicy because if you notice, let's route it all the way to up here. If you notice, the N and P sides are on the wrong bits of the chip, so you'll need to use a via in order to cross from one side to the other. And so you can do that by just adding a via. The button for that is up here. You can click Place Via. And then it's actually, vias by default are a little bit large. You can make them smaller, but it's more expensive too, so we'll just go with the Altium default. And then we can like make this via carry whatever like signal we want. So if we double click on this like hunk of wire, it'll tell us. Actually, let's yeah, we can see that this hunk of wire is connected to like DN over here. So we will take this via and then change it if it'll let me. There we go. We pull up properties for the via. If we can change what net it's connected to. I'm going to make this one be connected to DN And then if we notice now, there's a little air wire going between the via and the trace itself, and so we can use that to route through the via, go to the bottom side, and then come up over on the other side. If that makes sense. Yeah? Just in general, you usually want to minimize them. Back in the olden days, it used to cost money to put a via on the board. That has generally since passed. But when we put a via on there, like that's a hole that goes through the whole board, right? And so if we wanted to route a connection on the bottom side of the board, we couldn't, like in that same space, because there's a via like occupying that section of the board. So generally, you want to keep them like a little bit sparse for that reason. So you get so it's just easier to route. And depending on how you do some things with your ground planes, it can also cause like some weird signal problems. But generally, we'll say it's convenience for now. Yeah. Okay, let's try that. Let's rotate U2. So now it's over on the other side. I'm going to reset my error markers. And then let's go ahead and let's go ahead and remove these traces. I could go through and click every single part of the trace and delete it. That's really annoying. So instead, I'm going to use a tool called unroute. If you go to the route menu and then hit unroute and then connection, you just click on the bit that you want to remove, and there you go. The shortcut for that is UUC. The shortcuts start coming after a little while. Cool, so let's go ahead and route that differential pair again. And if we try and put those over here, let's just put them up to here. And oh, hey, we have the same problem. What we could do is if we were trying to be really fancy, we could have some whisker-thin traces that try and go on the back side of the chip here and sneak in from the bottom. But this chip has a chunk of exposed metal on the bottom side for grounding. And so we could pay extra to our manufacturer and for that whisker-thin trace over here and just cross our fingers and hope it doesn't short to anything as we try and sneak it under the chip. Generally, manufacturers don't like you doing that, so it's better to just put a via in, cross it, and then go ahead. Does that make sense? Sweet. Yeah.
One thing you could do if you wanted to, I wouldn't suggest it, but if you really, really care about getting that differential pair the exact same length, sometimes what people will do is they'll stick if you have a through hole connector for your CAN bus on one side, or your differential pair on one side, and you take that chip and you put it on the bottom of the board, that will flip the leads of your differential pair, and then you can route it straight. Maybe you don't want to do that depending on what else is coming out of that chip. Maybe you do. It depends what are the advantages and disadvantages of putting that chip on the bottom side of the board. Here, if you were to do it here, you would have to put two vias right where the connector are to go through the board and then route the differential pair that way. I don't actually know what the signal integrity implications of that are, but...
Go ahead.
So I know someone asked where you shouldn't put a via. Usually in cases like this USB or on the audio side, what happens is that when you route a via and you have your trace going to a via, that via is going to have a different impedance compared to the trace that you have. So as the signal goes to that via, it's going to cause weird reflections and all that. So for the most part, you want to avoid it as much as possible. You can still do it. You just have to model the impedance of the via, which is coincidentally what I'm doing right now. But yeah, avoid it at all costs.
That starts to matter a lot more as you go to higher and higher frequencies. USB is pretty quick in terms of frequency because we're that's how I'm putting HDMI signal out on the monitor right now. So USB cares a lot, especially Type C and such. For some other signals that are a lot slower, you might not actually care. The I2S signals between the DAC and the microcontroller are a slightly lower frequency, so it won't bite you as much, but you still generally don't want to route it through too many vias. Cool. And to Addy's point about just flipping the part over, I do want to show you how you would do that. For this chip, we don't, like in the real world, we wouldn't want it to live on the other side of the board because that'd just make it hard to put together. But if you are like, if you have like the part selected and you want to put it over on the other side of the board, you can hit Control L if the VM will cooperate. If you hit Control L, hello? Might just be L. Oh yeah, it's just L, okay. Sweet, this is now turned blue because blue is this color of the copper layer on the bottom side of the board. And so now if we have a look, I'll clear the error markers. Now these are going in like exactly the right spot, and we could put 2 vias next to it and then route on the bottom side. Cool. You'll want to do this for your battery holders, most likely, because we could route we can have a bunch of parts on the top side of the board, and then just stick the batteries on the bottom. That's a gentle suggestion. It's what we did on the staff reference design in order to keep things like nice and tidy. Cool. Anything else you all are wondering about? Yeah. Sorry? Oh, yes. For trace width, you can do a number of things. If your traces already exist on the board, you can see what the width is in the properties menu. So like over here, we're looking at the properties panel. And I selected this trace, and it says 15 mil. We could change that if we wanted to. Let's say we want to make it 10. It'll happily comply. You can also change the width of the trace as you're routing it. So let's say that I wanted to route this differential pair down here, but if you notice on the side, over here, it says 15 mil. I could change the trace width as I'm routing it, and let's say I wanted to make it, I don't know, something like 5. I could hit 5. Oh, I see what's going on. Out of the box, Altium won't let you make your traces super, super tiny. And I believe the default limit is 10 mil. So we're just going to give it 10. Let's pick a non-differential pair, because I think it's being weird about that. Whoop. Okay, so now we're just we're routing some generic trace. And you can see over on the side, the width is set to 10. We could increase it, maybe make it 20 if we wanted to. Hello? You might need to update your rules to allow it. All right, sorry, that's being a little bit weird. Yeah, sorry, that's where you would update it. Sometimes Altium will get a little persnickety about what trace widths it will allow and which ones it won't. If you run into troubles there, talk to us on Piazza. I think we had somebody have a similar problem. There's a answer posted, but you can go ahead and go to Tools and then hit, it's Design and then Rules. And this will bring up all of the rules that Altium is trying to enforce on your design. If you go to Routing, and then hit width, we can see everything that it's trying to do here. And here it says minimum width is 10 mil, maximum width is 10 mil. Okay, so that's why I can't change it to anything else. Cool. Yeah? There is a shortcut for it. I don't remember it off the top of my head. Hit the trace and then hit tab. You're right. Cool. Yeah, go ahead. Sure. So there's a little bit of a distinction to make here. Normally, when we're doing 2-layer boards, power and ground planes are something that we care a lot about on multi-layer boards. If we've got a 4-layer board, a lot of times the methodology that you'll see is you'll have top copper, and then an internal layer, and then a bottom layer, And normally what people will do is make the top and bottom layers signal. And then like parts will mount to the tops and bottoms of the boards. And then the inside will pick one layer to be power and one to be ground. And what this lets us do is it's a convenience thing, right? Like if we have some part on the top here that needs power and ground, we just drop a via next to the power pin and next to the ground pin, and there we go. Make sure our bypass caps are nice and close, but that's the setup for it. This is a 4-layer board, right? But we're asking you to make 2-layer boards because we want to like tame the complexity of what you're working on. So a lot of times what we'll settle for is instead of a power plane, which these are, because the entire layer, the entire plane, is either power or ground, instead we'll settle for something called a ground or a ground pour or a power pour. And that's different because we're going to look at the top view of a board here. Let's say we have our top layer copper, and we have a bunch of like parts that need to connect to each other. And so on. And they have all their signals routing between them, and a bunch of stuff. Maybe this goes to like some component over here. We have all of our signals up here living inside of the top layer. What we do in order to make a ground or a power pour is we take all the space that isn't occupied by either the like pads here and the traces, basically all the unoccupied copper, and we just dump more copper over the entire thing. And we fill up all the unoccupied space with more copper. And then we connect that all to one thing. And if you connect it to ground, it's a ground pour. If you connect it to power, it's a power pour. In the reference design that we gave you, we put a ground pour on the bottom layer. So on the top, it's nice and sparse. You just see a bunch of stuff like this. And then on the bottom, we have only a handful of traces, but a massive ground pour. Depending on your exact situation, generally it's preferred to have a ground pour on the bottom and top layers of our boards. For the reference ones that we gave you, for a couple of reasons, we decided to only do it on the bottom layer. But when y'all route yours, you're welcome to put a ground pour on the top and a ground pour on the bottom if you so desire. We don't really have space for a power plane in here because this is a 2-layer board, and planes really exist for like multi-layer stuff. Does that hopefully make sense? Okay, sweet. You probably want to know how to put that in Altium. Oh, like instead of just a big wire that goes around here and just connects everything? Oh, that's an excellent question. Let's say I have this part over here, and let's say this is connected to like ground, and it needs to connect to, there's some other part over here that's also like connected to ground. If I have a long, like thin piece of copper over here, what circuit element does that look like? It's like a little resistor, right? So as stuff is consuming power, all the current that goes into it has to come back out of it, right? And so parts, let's say I have an LED or something that I'm powering. This side would go to maybe some kind of resistor, like you saw in lab 1. This side would be power. This side would be ground. So any current that goes in on the power side has to come out on the ground side, right? So we're actually putting a decent amount of current through here. But if we have a long, thin trace, this isn't actually an ideal connection. This turns into a little mini resistor. And so now the voltage, like what we thought was ground over here, isn't really. The ground that we want to place here is not the same as the ground over here. And so this will cause problems, especially in digital circuits, where having a precise, or actually analog ones too, where having a very precise like ground reference is incredibly important for your circuit to operate. So that's why we use just a massive piece of copper. It can come with some other weird constraints too, like with signal reflections and other high frequency stuff, but like for most stuff that isn't like weird, that's the reason. Cool.
Just real quick to add to the 2 places I think you would use like really close to each other especially because like board cost goes quite significantly with board area. So when you're manufacturing at scale, like packing those components as tight together is very useful. And then what you would do, power plane and ground plane, you have a via basically as close to that ground pin as possible. Just send the ground straight down to the plane. And then also, like Fischer was saying, with the references, a lot of the time what will happen is when you have super precise analog sensing requirements, or like if you're doing current sensing, or like, because there's some current sense boards that measure in the terms of like nanoamps and stuff like that, or for like the very precise sensing applications, you kind of want smooth, steady planes where your current is running through, because it just minimizes, like your cross-sectional area is massive at that point. So they'll use like a thick plane and also a very wide plane to get that ground as smooth as it possibly can be. And then it's just the resistance of the via, which they can account for by testing the via. Like you can get specs on what impedance you want your via to be, and once you have that, you can account for that resistance in whatever calculation you're doing to measure your signal, and then your ground plane effectively has negligible resistance. That makes sense.
Cool. Sounds good. Other questions? Things that don't make sense. I can do a quick demo of how to put a ground pour in Altium if you would like. That'd be useful. Gentle nods? Okay. Excellent. So there's not that much going on in the bottom layer on our board here right now. We just have that one part just chilling over there, and also the via. So this is not going to have a very interesting ground plane or a ground pour just yet, but we'll throw it in there. Let's zoom in over here. Cool. What let's do is let's go to Tools, and then Polygon Pours, Polygon Manager. And I know I'm throwing a lot of just like tool-specific menus and stuff at you. Stuff is in the documentation, and also if you like get confused or feel like there's like that there should be an easier way to do something, there probably is. Ask on Piazza. We'd love to help you save time. But cool, we have our Polygon Pour Manager, and we'll just go ahead and hit New Polygon From, and then we have an option to either make it from like some shape we've already given it, or just the board outline. We'll hit the board outline. And right now our board is just a square, so it's just going to make a square. We want this to live on what layer? The bottom layer. And what do we want it to connect to? Ground. So I'll type ground. And then it needs a name, because NoNet LO1 P00 is boring. Let's give it a good name. What's a good name? Reese. I'm digging it. All right, so we'll do that, and then let's go ahead and apply. And it's just going to tell us that any changes we've made are going to go to the design. Excellent. All right, so we put down our pour here, and as you can see, it flooded the entire thing, with some exceptions. So the via over here has a little bit of a spacing around it, right? Because like if we had the ground pour right up next to that via, we'd short the via to ground, which we don't want to do. The via belongs to DN, not ground. So that's why we have a little cutout in the clearance there, just so we don't accidentally connect it. If we scroll down, we can notice that like on the USB connector, some of the little like pins on the output. Let's see if we can get 3D view of that. Not easily. You'll notice that like those are connected to ground, and we now have these little like star connections to those points. The reason why it's a star is because of some thermal stuff that's a little weird. But it's fine to leave that for now with the Altium default settings. But it's connected that all to ground for us. We now do not have to like take a nice windy trace around the board in order to connect all the grounds together. The pour has done that for us. And it also has the clearance around it as well. Cool. Does that hopefully make sense? Sweet. One other thing I do want to mention here is like if we go ahead and move the part, like if we just drag this over here, now this is going to complain because it's saying like, oh, like I'm not really connected to ground because there's like a pour underneath me that like isn't updated. If you want to update your ground pour, go ahead and just like go to the same place in the menu, Tools, Polygon Pours, and then just hit Repour, Repour All. And it'll go ahead and compensate for whatever change you just made. Cool. Does that check out? People believe it? Excellent. Going to be showing all your friends how to make ground pours. Delightful. All right, what else? What else you got? Yeah. Like a via for all the ground stuff here. Kind of the same reason as like before. If we wanted to do a, sorry, I'm not sure I understand what you're saying. Like when you say that we have like a via there, is that like a thin windy trace that like connects to a via, and then the via goes to what? Oh, yeah, you can do that. You can have a pad and then a via that just lives like right on the inside of it. And like manufacturers will let you do this. This is like a cross section of the board. The via lives here, and then this whole thing is just made of copper. In general, you don't really want to do this for a couple of reasons. The first being like it's a little hard to manufacture. Most like factories have gotten around that by now. But the primary reason is remember, well, what did we do yesterday in lab? What was the first part of the lab that we did? We stenciled our boards, right? We put solder paste on the whole thing. If I go to assemble this and I put a thin layer of solder paste on the whole thing, and then I have this nice little hole that's made of metal here, what's going to happen when I reflow? Where's the solder paste going to go? It's not your question. It's okay. Where's it going to go? It's going to go in the hole, right? Like this whole thing is going to get plugged up. Whole thing. It's going to get plugged up with solder, right? So is there going to be any left on the pad? No, not really. There's going to be a little bit, depending on how much went in the hole and whatnot. But like, it's all going to go in here. There's not going to be a ton on here. And then now our part isn't as secure as we would have wanted it to be otherwise. You can get around this by asking your manufacturer to fill these holes and plug them for you. That's called a plugged via. But you have to pay for it. And usually just fixing your board so that you just move the via super close to the pad but not on the pad is like cheaper in terms of like overall cost than this. At least for the stuff that we're working on. If you are Apple trying to make the iPhone like 27, you will probably consider these. Cool. Anything else people are wondering about? Yeah. Usually, yes. You can actually, there's some cute tools for this. Normally, when I'm doing layout, I will do like placement first and then routing, but I'll route all the signals first, and I kind of just won't consider power and ground until the end of things. That obviously changes a bit. Like if you're doing the boost converter, the whole point of that chip is power and ground, so you probably want to care about it there. But if you're just doing generic signal, what you can do is go in here, and if you go to net actions after right-clicking something, you can hit show or hide nets, and that'll choose whether or not the power and ground shows up in your rat's nest. So right now I think it's disabled. I could hit show nets, and oh, now we have this big like meandering bit that goes everywhere throughout the board. That might not actually be useful to you when you're like placing parts and stuff. So you can hide it if you want. So we could go over here, right-click, net actions, hide net, and now it's gone from the rat's nest. But yeah, you have a lot of flexibility there. Altium will kind of just like move around to whatever you want to do. Cool. What else are people thinking about? The purpose of today's lecture is just to like generally answer questions and just orient ourselves a bit, because we don't want you to be super lost and confused with layout. So feel free to like head out if you like whenever you'd like to, but I'm happy to like stick around, just keep answering questions. We've got like 15 minutes left until class would normally be over. Yeah. I wouldn't necessarily say as square as possible. I would say just like make it in whatever shape is most natural for the room. Because if you make it as square as possible, you might run into some situation where like you really had to work hard in order to get like the amplifier into a square when the shape that it really wanted to be was like something like this maybe. Sure. And then maybe this part actually like fits into your board layout better than this would. So don't expend a ton of effort trying to turn this into this before you're sure that you actually need it. Yeah. Boxes are nice because Altium like has a grid system, so a lot of stuff will look boxy. But listen to your design. It's trying to speak to you. If it wants to be this shape, just let it. It's okay. Cool. Yeah. Yes. Mm-hmm. Yes, and we didn't exactly tell you what the exact current of every single signal in the design was, right? For the most part, it's okay to leave things at the default here. 10 mil of copper will handle, correct me if I'm wrong, but it'll handle about like an amp of current with like a 20 degree C like temperature rise on the outer layers. So all that to say, 10 mil is generally okay. There's a reason it's the default in Altium. You can stick with that for the moment. Sometimes you might want to change that a little bit. Let's say if we have the trace from the boost, what's our output of the boost converter? What does it make for us? 12 volts, right? And where does that go? Well, just the amplifier. So maybe our boost converter to our amplifier, maybe this trace between here, we could leave it as a 10 mil trace, but it might heat up a lot, or it might get a little bit of voltage drop because it's a tiny little resistor. We could just beef in this trace up to whatever we want. Let's say that the output on our boost converter is like, well, you know how we had that inductor? It's got like a little pad there and a little pad here. Well, these are like physically large, right? Like I think this one is like something like 50 mils. And then over here on the amplifier, we have like our big capacitors for bypass, right? So that'll be like maybe here or something, right? What we could do is just do a 50 mil trace from here all the way over here if you want. So like that'd be a reasonable cause for making it a bit larger because this carries a lot of power. A cause for making it a bit smaller is, let's say you have a chip that has some really tight like pin spacing, and like each one of these guys is like only 8 mil like tall, something like this. Maybe that's only 8 mil. If we try and put a 10 mil trace in there, we'll get something that kind of looks like this, right? And if we try and put these next to each other, oh no, my traces are on top of each other. That'd be a good cause for making that smaller, because if any of those pins were designed for a lot of current, the manufacturer probably would have put a bigger hunk of metal on it, right? So if the manufacturer says that, like, yeah, 8 mil is fine for the actual part, then that's a good suggestion for maybe you only use an 8 mil trace there. Does that check out? Sweet. Yeah.
One other thing that's kind of trace sizing real quick is like on the lecture notes, you'll notice like we put a table there of like this amount of current should have this trace thickness at this weight of copper and stuff like that. One thing to consider when you're taking those tables is don't take for granted the fact that they probably don't have a safety factor. A lot of the time what those tables are doing is they're saying based on pure theoretical calculation, like this piece of copper will hold 3 amps, and more than 3 amps it will explode. So oftentimes you'll probably see like higher, like larger traces even when the table says it doesn't need to be that thick, because what engineers will do is we'll take like if a 3 amp trace needs to be like, I don't know, 10 mil, we'll make it at least 15, if not 20 to 25 because of that safety factor. You want, I usually go with at minimum a 1.5 times safety factor, if not a 2 times or higher safety factor. And for like really high current stuff, I'm sitting there with like a 8 times safety factor because you really don't want it to fail. So that's another, like, I don't know if I just want to throw that out because I don't know if we've mentioned safety factors at all.
Yeah.
And that concept also applies to everything we design, right? So like, especially when you're picking
There's also the lovely upper bound on like making things large, where it's like as large as you can physically make it while not being like too ridiculous. Like if I have the boost, like if I have the output of the boost converter and the input of the amplifier, I could also just take a 100 mil trace and just go around like this entire thing. That's also valid, and I've done that before. It looks a little stupid, but like if you don't want to bother with current calculations, you know, maybe that suits your fancy, or maybe you're too ashamed to even consider something like that. Cool. Any other questions? We're about 5 minutes out from when we normally start. Yeah. There's some.
Like, we need the components to be very close together.
Yes.
Like, do you always have to smush them together, or do you want like a little bit of space just for like practical considerations of putting on the board?
That's an excellent question. The question is, do we put components as close together as we can all the time, or do we ever want space between the two? Sometimes you want them to be super close, like for all of the digital stuff. Like digital signals are pretty resilient to noise, so those can all be like pretty close together, at least for the frequencies and the stuff that we have going on our board. You can put those reasonably close together in order to save space. That's totally okay. For other stuff, like let's say we are trying to make, I don't know, let's say we're looking at like the microcontroller that we have on our board. It's like an ESP32, and it's got like that Bluetooth modem, and then there's like a CPU next to it, and then there's like an antenna over here, right? The symbol for an antenna looks like this. Let's say we have all this stuff going on. We want the antenna to be like nice and isolated from the rest of the system, right? Because otherwise, all the noise from our CPU, like going beep, boop, 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 beep, beep, will like get into our antenna, and it'll make it really hard to like receive Bluetooth, right? Like we're gonna have a bunch of noise that like couples over through here. And there's a couple ways you can get around it. If you've taken 608 here, you know that like the microcontrollers we give you have what kind of antenna? Is it on the board, or is it external? It's external, right? Like we can physically just yeet the like antenna away from everything else. What we could also do is just put a big metal shroud over this whole thing and drop a Faraday cage around it so that we have less noise propagating between the antenna and everything going on over here. So there's a case for like separating the two, and there's other ways to like mitigate that as well. Does that check out? Sweet. Cool. Anything else? All right, delightful. We're basically at time. If you have any other questions, feel free to come talk to us afterwards. Good luck with layout. It's going to take you a little bit. Make yourself a nice cup of tea. Have a lovely, sit down and just have a lovely little Altium session. We're going to be around on Piazza. We've got office hours as well if you have questions. And yes, hopefully this was useful to y'all. Cool. Thank you.